We call it Earth, but that name has always been a quiet lie. 71% of this world is ocean. If an alien civilization were to catalog our planet from a distance, they would not call it Earth. They would call it water. Or perhaps more honestly, they would call it unknown. Because beneath the surface of our seas lies a realm we have barely touched. A place so vast, so hostile, and so hidden that we know more about the craters of Mars than we do about the valleys that stretch beneath our own waves. It sounds impossible, absurd even. How can we claim to understand distant galaxies while remaining strangers to the depths below our feet? The answer is simpler than you might think, and far more humbling. Space is empty, the ocean is not. Let's begin where most maps end, where the light dies and the pressure begins to build into something unimaginable. The ocean has layers, just like the atmosphere. We know the surface well enough, we swim in it. We sail across it. We've measured its currents and studied its storms. But go deeper, past the sunlit shallows, past the twilight zone, where the last rays of blue surrender to black, and you enter a world that might as well exist on another planet. The abyssal zone begins at 4,000 meters. That's twice the height of the tallest mountains on land, only inverted, flipped upside down. A chasm carved into the crust of the earth where no sunlight has ever reached. And it goes deeper still, the Hadal Zone, named after Hades, the ancient Greek underworld. It begins at 6,000 meters and descends all the way to the ocean's absolute floor. Nearly 11 kilometers down in places, 11,000 meters of water pressing down on itself, on the rock below, on anything foolish or brave enough to venture there. To put that in perspective, if you took Mount Everest and dropped it into the Mariana Trench, its peak would still be more than 2 kilometers underwater. This is not some minor corner of our planet. The abyssal and Hadal zones make up the majority of Earth's biosphere, the largest habitat on the planet. And we've barely seen it. Only 5% of the seafloor has been mapped with modern precision. 5%. The rest is educated guesswork, sonar pings, and statistical models. We've constructed higher resolution maps of the Moon, of Mars, of distant moons orbiting Jupiter than we have of the trenches that lie just beyond our coastlines. Why? Why does the deep ocean remain so elusive? Because the ocean is not empty. It is full of water, full of weight, full of crushing, unyielding force. Space is a vacuum, a void. The challenge of space is not pressure, it's the absence of it. A spacecraft needs to hold air in, to keep a tiny bubble of Earth-like atmosphere intact while floating through nothingness. It's a balloon, essentially. A sealed environment designed to resist the pull of the void. But in the ocean, the challenge is reversed. The ocean doesn't pull, it pushes. With every meter you descend, the weight of the water above you grows. At 10 meters, the pressure has already doubled. At 100 meters, you're experiencing 10 times the pressure you feel at sea level. At 1,000 meters, the water is pressing down with the force of 100 atmospheres. And in the Hadal zone, at 11 kilometers down, the pressure exceeds 1,000 atmospheres, over 8 tons per square inch, enough to crush steel like aluminum foil, enough to compress even water itself into something denser, stranger, colder than it should be. Engineering for space is difficult. Engineering for the deep ocean is nearly impossible. Consider a satellite. Once it's in orbit, it stays there. There's no weather in the vacuum, no wind, no waves, no forces trying to tear it apart. It just glides, weightless and free, following the curve of gravity around the Earth. Solar panels can stretch out like wings. Instruments can be delicate. There's no corrosion, no rust, no salt eating away at every surface. But a deep-sea submersible? It has to be built like a tank, like a bomb casing, really. Thick walls of titanium or carbon fiber, spherical hulls to distribute pressure evenly. Every joint, every seal, every window is a potential point of catastrophic failure, Because if something breaks at depth, there's no time. The ocean doesn't give warnings. It simply crushes, and you can't just build it once and leave it down there. Every descent is a round trip. Every mission taxes the materials, metal fatigues, seals degrade, salt corrodes relentlessly. The ocean is not just hostile, it's actively destructive. This is why we've sent more people into space than into the deepest parts of our own ocean. Hundreds of humans have been to orbit, 12 have walked on the moon. But only 4 people have ever reached the bottom of the Mariana Trench. 4. In the entire history of human exploration. Let that settle for a moment. The moon is 384,000 kilometers away. The Mariana Trench is 11 kilometers down. One is an impossible distance across the void. The other is a short trip, geologically speaking, through the only substance more abundant on Earth than rock. And yet, the moon is easier. But pressure is only part of the story. There's another barrier, one that's even harder to overcome. Darkness. The ocean is opaque. Light, the tool we rely on for almost all of our exploration, dies within a few hundred meters of the surface. Water absorbs photons. Red wavelengths vanish first, then orange, then yellow. By the time you've descended 1,000 meters, even blue light, the most penetrating visible color, is gone. What remains is absolute blackness. On land, we see with light. In space, we see with light. Telescopes gather ancient photons from distant stars. Satellites photograph planets in exquisite detail. The Hubble Space Telescope can resolve galaxies billions of light years away because space is transparent. Light travels unhindered through the void. But in the ocean, light is useless. You can bring your own, of course. Submersibles carry floodlights. Remotely operated vehicles sweep beams across the seafloor like wandering eyes in the dark. But those lights illuminate only what's immediately in front of them, a cone of visibility stretching a few dozen meters at most. Beyond that, nothing. Just blackness pressing in from all sides. It's like trying to explore a continent with a flashlight. One small circle of light in an endless night. You see only what you're pointed at. Everything else remains hidden. This is not how we explore space. We don't need to visit every asteroid to map the solar system. We don't need to land on Europa to photograph its icy surface. We point our telescopes and cameras and let light do the work for us. But the ocean swallows everything. Visible light, radio waves, even most electromagnetic signals, they all get absorbed within meters. The only thing that travels well through seawater is sound, so we've learned to see with our ears. Sonar, sound navigation, and ranging. We ping the depths with acoustic pulses and listen for the echoes. The time it takes for sound to bounce back tells us the distance. The shape of the echo tells us the texture. Rocky, smooth, sloped, flat. It's an elegant solution, but it's also imprecise. Sound waves spread out as they travel. They reflect off layers of temperature and salinity. They scatter. They distort. Mapping the ocean floor with sonar is like trying to paint a portrait by shouting at it and listening to how your voice bounces back. You can get the general shape, but the details, the fine features, those remain blurred. And there's another problem, one we don't talk about enough. The ocean is big, absurdly, incomprehensibly big. Space feels infinite, and in a meaningful sense, it is. But we can point our telescopes anywhere and gather light. We can scan the sky systematically. We've mapped millions of galaxies, cataloged billions of stars, identified thousands of exoplanets, all without leaving Earth's surface. The ocean offers no such luxury. Every square kilometer of seafloor must be measured individually. Every trench must be descended into. Every ridge must be mapped with painstaking passes of sonar. There are no shortcuts, no distant observations, no photographs from orbit that reveal everything at once. The seafloor is 360 million square kilometers of rock and sediment. Most of it has never been seen by human eyes. Most of it never will be. We've mapped Mars, we've mapped Venus, we've mapped Titan, a moon of Saturn hidden beneath a thick atmosphere of methane and nitrogen. But we haven't mapped our own ocean, not because we don't want to, not because it isn't important, but because the ocean is crushing, corrosive, dark, and vast, because it resists us, because it was never meant to be known. And yet, we keep trying. Because somewhere down there, in the trenches and the abyssal plains, in the volcanic ridges and the cold seeps, there are answers. Answers to questions we've been asking since we first looked up at the stars and wondered if we were alone. The deep ocean may be harder to reach than space, but it's closer, and it's ours, if we can ever learn to see in the dark. There's a creature that lives in the deepest trenches of the Pacific Ocean. It has no eyes, no pigment. Its body is pale, almost translucent, built from tissues so fragile they would collapse under their own weight if you brought them to the surface. It's a snailfish, a small, gelatinous thing that glides through absolute darkness, 7,000 meters below the waves, in a place where the pressure would instantly pulverize almost any form of life we know, and yet it thrives. When scientists first captured footage of these fish, they didn't believe what they were seeing. How could something so delicate survive in conditions so extreme? How could life exist at all in a place so hostile, so removed from everything we thought was necessary for survival? The answer is humbling. Life doesn't need our permission. It doesn't wait for ideal conditions or convenient circumstances. It simply finds a way. And in the deep ocean, life has found ways we're only beginning to understand. We've spent centuries cataloging the creatures of the land and the shallow seas. We've named millions of species. We've categorized them, studied them, mapped their habitats, and traced their evolutionary histories. We thought we had a decent grasp on the story of life on Earth. Then we went deeper, and we realized the story was far from finished. The abyssal and hadal zones are not barren wastelands. They are not empty voids waiting to be filled. They are ecosystems, strange, alien, astonishingly diverse ecosystems that operate on principles we're still struggling to comprehend. Consider the supergiant amphipod, a creature that looks like a pale, oversized shrimp, but can grow to nearly 30 centimeters long. That's 50 times larger than its shallow water cousins. Why? We don't fully know. Perhaps it's the cold, perhaps it's the pressure, perhaps it's the scarcity of food that favors organisms with slower metabolisms and longer lifespans. Or consider the Dumbo octopus, named for the ear-like fins that flutter on either side of its head. It hovers above the seafloor like a ghost, pulsing gently through the darkness, feeding on worms and crustaceans that burrow in the sediment below. These are not exceptions. These are just the ones we've found. How many species live in the deep ocean? How many forms of life have evolved in the dark, under pressures that would crush a submarine, in temperatures barely above freezing? We don't know. We have fragments, glimpses, a few hundred documented species from the hadal zone, a few thousand from the abyssal plains. But these numbers are almost meaningless. Every expedition brings back something new, something unexpected, something that forces us to revise our assumptions about what life can be. A recent study estimated that we've likely discovered less than 10% of deep-sea species. 10%. That means 90% of the life in the largest habitat on Earth is still unknown to us, still hidden, still waiting to be found. Imagine if we applied that same ratio to space. Imagine if we'd only identified 10% of the planets in our solar system. We'd consider our knowledge embarrassingly incomplete. We'd demand more missions, more funding, more urgency. But the deep ocean? It remains an afterthought, a mystery we acknowledge but rarely prioritize. And the most astonishing part? The existence of deep-sea life at all was once considered impossible. For most of human history, scientists believed the deep ocean was lifeless, a cold, dark desert crushed under unimaginable weight. They called it the azoic zone, the zone without life. It made sense. No sunlight meant no photosynthesis. No photosynthesis meant no plants. No plants meant no food chain, no foundation for life to build upon. The logic was sound, but it was wrong. In 1977, a team of scientists aboard the research submersible Alvin descended to a volcanic ridge in the eastern Pacific. They were there to study geothermal activity. They were not expecting to find life. What they found changed biology forever. Hydrothermal vents, cracks in the seafloor where superheated water, heated by magma deep within the Earth's crust, comes roaring out into the freezing ocean. Water so hot it should be steam, kept liquid only by the crushing pressure of the depths. And surrounding these vents, against all logic, against all expectations, was life. Not just microbial life, not just bacteria clinging to existence in the margins, but thriving, complex ecosystems. Tube worms 2 meters long, their blood-red plumes swaying in the current, clams the size of dinner plates, ghostly white crabs crawling over mounds of minerals, shrimp swarming in clouds so dense they looked like smoke. This was life without sunlight, life that had no connection to the surface world, life powered not by photosynthesis, but by chemosynthesis. Let that concept settle. On the surface, almost every living thing depends, directly or indirectly, on the sun. Plants capture light and convert it to energy. Herbivores eat the plants. Carnivores eat the herbivores. The sun is the foundation, the starting point, the source of nearly all energy in the biosphere. But at hydrothermal vents, the sun is irrelevant. Here, bacteria harvest energy from chemicals in the vent fluids. Hydrogen sulfide, methane, iron, compounds that would be toxic to most surface life become fuel. These bacteria don't need light, they need chemistry, and the Earth provides it endlessly through volcanic activity that has burned for billions of years. The tube worms don't eat. They have no mouths, no digestive systems. Instead, they host colonies of chemosynthetic bacteria inside their bodies. The bacteria produce energy from the vent chemicals, and the tube worms absorb the nutrients they create. It's a partnership, a symbiosis born in absolute darkness, and it's everywhere. Since that first discovery, we've found hydrothermal vents in every ocean, on mid-ocean ridges, on volcanic arcs, in the deepest trenches. Each one is an oasis, an isolated world that operates on entirely different principles than the sunlit surface. Some scientists now believe that life on Earth may have begun at these vents, that the first organisms emerged not in shallow tidal pools warmed by the sun, but in the crushing darkness of the deep ocean, powered by the heat of the planet itself. If that's true, then the deep ocean isn't just a strange habitat for unusual life. It's the cradle, the birthplace, the origin of everything that followed. But even that might not be the full story, because beneath the seafloor, beneath the rock itself, there may be even more life than we ever imagined. It sounds absurd. Rock is not alive. Rock is solid, inert, lifeless. But drill deep enough and you start finding things that challenge that assumption. Microbes, bacteria and archaea living in microscopic pores and fractures in the rock, sometimes kilometers below the seafloor. They don't move. They barely metabolize. They exist in a state so slow, so minimal, that calling it life almost seems generous. But it is life, and there's a lot of it. Some estimates suggest that the biomass of this deep biosphere, this hidden world of microbial life living inside the Earth's crust, may rival the biomass of all the forests on land, maybe exceed it. Think about that. All the trees, all the plants, all the visible green photosynthetic life that covers the continents. And beneath the ocean, buried in rock, there may be just as much living matter, maybe more. We don't know how deep it goes. We've drilled as far as 2 kilometers below the seafloor and still found living cells. Could it go deeper? 3 kilometers? 5? 10? We don't know. We don't know how these organisms survive. We don't know what they eat, though we suspect they derive energy from chemical reactions between rock and water. We don't know how long they live. Some might have generation times measured in centuries or millennia. We don't even know if they're truly isolated or if there's some exchange, some connection between the deep biosphere and the ocean above. They could be remnants, ancient life trapped when the seafloor formed, sealed away and forgotten. Or they could be pioneers, the first wave of colonization into a realm we didn't even know existed. Either way, they force us to reconsider what life is, where it can exist, what it needs. For most of history, we've defined life by what we could see, by movement and growth and reproduction, by ecosystems that fit into narratives we could understand, predators and prey, sunlight and seasons, birth and death in recognizable rhythms. But the deep ocean has shown us that life is far stranger, far more resilient, and far more inventive than we gave it credit for. It exists in darkness. It exists under pressures that would destroy us. It exists without the sun, without movement, without anything we once thought was essential. And if life can exist here, in the most extreme environment on our own planet, then where else might it be hiding? What other impossible places might harbor something alive? The moons of Jupiter and Saturn have subsurface oceans locked beneath kilometers of ice. Could there be life there? Life that evolved in the dark, powered by the same volcanic chemistry we've found here on Earth? We used to think it was unlikely, but now we know better. Because we've seen what life can do when you stop telling it what's possible. And we've only just begun to look. There's a paradox at the heart of climate science. We can measure carbon dioxide in the atmosphere with extraordinary precision. We know how much we're adding every year through fossil fuels and deforestation. We know how much accumulates in the air. We can trace it, model it, predict its effects on temperature and weather patterns. But here's the strange part. When scientists add up all the carbon we've released and compare it to the carbon they can actually find in the atmosphere, the numbers don't match. There's carbon missing, a lot of it, billions of tons of carbon dioxide that should be warming our atmosphere, but isn't. It's somewhere else, somewhere we can't quite see. And the ocean is hiding it. The ocean absorbs carbon dioxide. We've known this for decades. When CO2 dissolves in seawater, it forms carbonic acid, which the ocean's chemistry can buffer and store. Phytoplankton at the surface absorb it through photosynthesis, just like plants on land. When they die, they sink. And as they sink, they carry carbon with them, down through the water column, down into the depths. This is called the biological pump, a vast, invisible engine that pulls carbon from the atmosphere and sequesters it in the deep ocean, sometimes for centuries. It's one of the reasons our planet hasn't warmed even faster than it has. The ocean is doing us a favor, a service we barely understand and rarely acknowledge. But here's what keeps climate scientists awake at night. We don't know exactly how the biological pump works. We don't know how efficient it is, or how stable. We don't know where all that carbon ends up, or how long it stays there. The twilight zone, that dim layer of water between 200 and 1,000 meters deep, is where much of this carbon vanishes. Particles of dead plankton, fecal pellets from tiny zooplankton, marine snow drifting down through the darkness. Some of it gets consumed on the way down by bacteria and small fish. Some of it dissolves. Some of it makes it all the way to the seafloor. But how much? And what determines whether carbon stays trapped in the deep ocean or eventually returns to the surface? We don't know. We have models, estimates, theories. But the twilight zone is vast and difficult to study. It's too deep for easy access, too large to sample comprehensively. We've measured it in scattered locations during brief expeditions with instruments that give us snapshots, not continuous data. And the stakes could not be higher. If the biological pump weakens, if warming or acidification or changes in ocean chemistry disrupt the organisms that drive it, then carbon that would have been locked away in the deep ocean will stay in the atmosphere instead. And our climate models, the projections we use to plan our future, will have been too optimistic. We need to understand the ocean not because it's mysterious or beautiful, though it is both. We need to understand it because it controls our climate, because it moderates our weather, because it determines whether our planet remains livable or slides into something far more hostile. And right now, we're flying blind. The ocean is not static. It doesn't just sit there, absorbing heat and carbon like a passive sponge. It moves, it circulates, it transports water and energy across the entire planet in patterns so vast and so slow that they took us centuries to even detect. Oceanographers call it the global conveyor belt, a system of currents that links every ocean on Earth. Warm surface water flows from the tropics toward the poles. Cold, dense water sinks at high latitudes and flows back toward the equator along the ocean floor. It's a loop, a cycle that takes roughly 1,000 years to complete. This circulation shapes our climate in ways most people never consider. Western Europe, for instance, should be far colder than it is. London sits at the same latitude as frozen tundra in Canada. Paris is level with Newfoundland. But Europe remains temperate, almost mild, because the Gulf Stream carries warm water from the tropics up along the eastern coast of North America and across the Atlantic. That warmth moderates the climate, melts ice, sustains ecosystems. Without the conveyor belt, Europe would be a very different place. But the conveyor belt depends on delicate balances, temperature, salinity, density. If the water at high latitudes doesn't get cold enough or salty enough, it won't sink. And if it doesn't sink, the circulation slows or stops. This has happened before. During the last ice age, meltwater from glaciers poured into the North Atlantic, diluting the seawater, making it less dense. The sinking stopped, the conveyor belt shut down, and temperatures in Europe plummeted within decades. It was a tipping point, a sudden shift from one stable state to another, triggered by a gradual change that crossed an invisible threshold. Could it happen again? Some scientists think it's already starting. The Atlantic Meridional Overturning Circulation, the AMOC, the northern branch of the global conveyor belt, has weakened by roughly 15% since the mid-20th century. Greenland's ice sheet is melting. Fresh water is pouring into the North Atlantic. The conditions that caused the circulation to collapse in the past are once again beginning to align. If the AMOC collapses, it won't just cool Europe. It will disrupt weather patterns across the entire northern hemisphere. It will shift tropical rain bands. It will alter monsoons. It will change the distribution of heat and moisture in ways we can't fully predict. And here's the most unsettling part. We don't know how close we are to that tipping point. We don't have enough data. We don't understand the deep currents well enough to model their behavior with confidence. We have sensors in scattered locations, but the ocean is enormous. The circulation is three-dimensional, layered, influenced by factors we're only beginning to measure. Internal waves, for instance. Waves that move through the ocean's interior, along boundaries between layers of different densities. They mix the water, bringing nutrients up from the depths and oxygen down from the surface. They transport energy. They influence the conveyor belt in ways we didn't even know to look for until recently. And we have almost no idea how they'll change as the ocean warms. This is the challenge. The ocean is not just big, it's dynamic, it's interconnected, and it operates on timescales that stretch far beyond human intuition. A change today might not show its full effects for decades or centuries. By the time we notice something has gone wrong, it may already be too late to fix it. But there's another mystery hiding in the deep ocean. One that's even more unsettling, one that involves a substance most people have never heard of, locked away in the cold sediments of the seafloor. Methane hydrates. They look like ice, pale crystalline structures that form when methane gas gets trapped in a lattice of frozen water molecules. They only remain stable under specific conditions: high pressure, low temperature, the kind of environment you find in the deep ocean or beneath Arctic permafrost. And there are gigatons of them, trillions upon trillions of tons of methane locked away in frozen deposits scattered across the seafloor. Methane is a greenhouse gas, a powerful one. Molecule for molecule, it traps roughly 80 times more heat than carbon dioxide over a 20-year period. Most of the methane currently in the atmosphere comes from natural sources like wetlands or human activities like agriculture and fossil fuel extraction. But the methane in the hydrates, that's something different. That's a reserve, a stockpile of potential warming, kept frozen and harmless by the cold, stable conditions of the deep ocean. The question scientists are asking is simple and terrifying. What happens if it melts? There's a hypothesis called the clathrate gun. It suggests that as the ocean warms, particularly in shallower regions or near continental margins, the methane hydrates could destabilize. The ice could melt. The methane could bubble up through the water and into the atmosphere. And once that happens, it would cause further warming, which would melt more hydrates, which would release more methane. A feedback loop, a runaway process that could, in the worst-case scenario, trigger rapid and catastrophic climate change. We know this has happened before. There's geological evidence of sudden methane releases in Earth's deep past, events that coincided with mass extinctions and dramatic shifts in global temperature. The Paleocene-Eocene thermal maximum 56 million years ago, a period when global temperatures spiked by 5 to 8 degrees Celsius in just a few thousand years. The leading theory is that methane hydrates destabilized, releasing enough greenhouse gas to push the climate into a new, hotter equilibrium. Could it happen again? Most scientists think a full-scale clathrate gun scenario is unlikely in the near future. The ocean is warming, yes, but it's warming slowly. Most methane hydrates are buried deep enough and in cold enough water that they should remain stable for centuries. Should. But we don't know for certain. We don't know how much methane is down there. We don't know how close the deposits are to their melting point. We don't know how the hydrates will respond to gradual warming or whether there are tipping points we haven't identified yet. And we're already seeing small-scale releases. Methane seeps have been observed off the coast of Alaska, off Siberia, off Norway. Some of them are natural, part of the ocean's normal geochemistry, but some might be the early signs of destabilization. We don't know, and that's the problem. We don't know how the ocean stores carbon. We don't know how stable the global conveyor belt is. We don't know how close the methane hydrates are to melting. We don't know because we haven't looked closely enough. We haven't invested the resources, the time, the attention that these questions demand. We've mapped the surface of Mars. We've sent probes to the outer solar system. We've detected gravitational waves from colliding black holes billions of light years away. But the engine that controls our climate, the vast, invisible machine that regulates temperature and weather and atmospheric chemistry, remains largely unknown to us. The ocean is not just a place, it's a process. A living, breathing system that has kept Earth habitable for billions of years. And we're changing it faster than we've ever changed anything, without fully understanding what we're doing. Perhaps it's time we started paying attention to the planet beneath the waves before we run out of time to learn its secrets. In 1997, the United States Navy dropped a network of underwater microphones into the Pacific Ocean. They weren't listening for whales or studying marine life. They were listening for submarines, for the quiet hum of propellers turning far below the surface, for the sounds of potential threats moving through the dark. What they heard instead was something else entirely, a sound, low, powerful, rising and falling over the course of a minute. It was picked up by sensors more than 5,000 kilometers apart, which meant it had to be incredibly loud. Louder than any biological source they knew of, louder than the largest whale, louder than anything that should exist in the ocean. They called it the bloop, and for years no one knew what made it. Theories emerged: a massive, unknown creature, something enormous living in the depths. An underwater volcanic event, iceberg calving. Eventually, scientists settled on the most likely explanation. It was the sound of a massive ice shelf fracturing in Antarctica, groaning and cracking as it broke apart and slid into the sea. But here's what the bloop revealed, more than any single answer ever could. The ocean is full of sounds we don't understand. We think of the deep ocean as silent, as a place of absolute quiet, where the darkness is matched by an absence of sound. But that's only because we can't hear it. The ocean is anything but silent. It hums, it clicks, it moans and rumbles and sings. It's an acoustic universe rich with signals traveling hundreds or even thousands of kilometers through the water. Sound is how the ocean speaks, and we're only just beginning to listen. Light dies quickly in seawater. Radio waves barely penetrate. But sound travels beautifully. It moves faster in water than it does in air, and it can propagate for astonishing distances, especially at certain depths where temperature and pressure create natural sound channels that guide acoustic waves like fiber optic cables. A whale singing off the coast of California can be heard by another whale near Hawaii. A volcanic eruption in the Indian Ocean can register on hydrophones in the Atlantic. The ocean isn't fragmented by distance the way land is. It's connected, linked by sound into a single, continuous medium. And it's full of mysteries. There are sounds recorded in the deep ocean that we still can't explain. Low-frequency hums that appear and disappear without pattern, pulses and clicks from unknown sources. The 52 Hz whale, a solitary creature whose calls are at a frequency no other whale uses, wandering the Pacific for decades, singing songs no one else seems to hear or answer. Is it a hybrid? A malformed individual? Or just different, calling out into the void, hoping for a response that never comes? We don't know. We've only been listening to the ocean for a few decades, and even now our coverage is sparse. A handful of hydrophones scattered across the vastness of the seas, recording fragments of an acoustic world we're only beginning to comprehend. But while we struggle to understand the natural soundscape of the ocean, we've already started filling it with noise of our own. The Industrial Revolution didn't just change the land, it changed the ocean too. And one of the most profound changes has been acoustic. Before the age of steam, the ocean was relatively quiet. There were natural sounds, of course, waves crashing, storms churning the surface, rain pattering down, the calls of whales and dolphins, the clicks of hunting tuna, the snapping of shrimp colonies. But these were organic sounds, sounds that had been part of the ocean's acoustic environment for millions of years. Then we added engines, propellers, massive steel blades churning through the water, generating low-frequency rumbles that travel for hundreds of kilometers. Shipping lanes crisscross every ocean now, and the cumulative noise from thousands of vessels creates a constant background hum. It never stops. It's always there, a baseline roar that marine animals have to navigate around, communicate over, somehow filter out. And it's getting louder. Global shipping traffic has increased exponentially over the past century. More ships, bigger ships, faster engines. The acoustic environment of the ocean has changed more in the last 100 years than it did in the previous million. But shipping noise is just part of the problem. Seismic air guns, used in oil and gas exploration, fire compressed air into the water to create shock waves that penetrate the seafloor. These blasts can reach 260 decibels, louder than a rocket launch, louder than a gunshot, at point-blank range. They fire every 10 to 15 seconds, sometimes for weeks at a time, mapping the geological structure beneath the ocean floor. Naval sonar, used to detect submarines, sends out pulses of sound at frequencies and intensities that can travel for hundreds of kilometers. Mid-frequency active sonar, the kind used by military vessels, operates at levels that can cause physical harm to marine mammals if they're close enough. This is not speculation. We've seen the consequences. Mass strandings of whales and dolphins have been linked to naval sonar exercises in the Bahamas, in the Canary Islands, in the Mediterranean. Healthy animals found beached and dying, their inner ears hemorrhaging, their tissue showing signs of decompression sickness, as if they surfaced too quickly, as if they were fleeing something. The debate in the scientific community isn't whether anthropogenic noise affects marine life. It's about how much and in what ways. Does it disrupt behavior? Absolutely. There's no question. Fish avoid areas with intense noise. Dolphins change their calling patterns. Whales abandon feeding grounds. But does it cause physiological harm? Does it injure? Does it kill? The evidence is mounting that yes, in some cases, it does. Sound underwater isn't just heard, it's felt. Water is dense, and sound waves carry energy. A loud enough sound doesn't just vibrate your eardrums, it vibrates your entire body, your organs, your bones. For animals that rely on sound to navigate, to hunt, to communicate, the rise of industrial noise isn't just an inconvenience, it's a crisis. And nowhere is this more evident than with whales. Whales are acoustic creatures. They live in a world shaped by sound. They use it to find food, to navigate across entire ocean basins, to maintain social bonds with individuals they might never physically see. Their songs carry for hundreds of kilometers, encoded with information we're still trying to decode. But now, their songs are getting lost in the noise. Imagine trying to have a conversation in a crowded room. At first, you can hear the person across from you. But as more people enter, as the volume rises, you have to raise your voice. You have to lean closer. Eventually, you can't hear them at all, no matter how loud you both shout. That's what's happening in the ocean. Whales are calling louder. They're changing the frequency of their songs, trying to find acoustic space that isn't cluttered with human noise. Some populations have shifted their communication to higher frequencies, abandoning the deep, resonant calls that once carried across oceans, but there's a limit to how much they can adapt. And the noise keeps growing. Blue whales, the largest animals ever to exist, communicate at frequencies around 10 to 40 hertz. Low, rumbling calls that can travel thousands of kilometers through the deep sound channel. But shipping noise occupies the exact same frequency range. The hum of propellers, the throb of engines, it's all happening in the same acoustic space where blue whales are trying to talk to each other. Their communication range has been reduced by 90%. 90%. Imagine if your ability to speak to someone was suddenly cut from 1,000 kilometers to 100. Imagine if the only people you could reach were the ones immediately nearby, and everyone else, everyone you used to keep in contact with across vast distances, just vanished into static. That's the acoustic world whales are living in now. And the effects go beyond communication. There's evidence that chronic noise exposure causes stress in marine mammals. Elevated stress hormones, suppressed immune function, changes in behavior that ripple through entire populations, mothers and calves getting separated, migration routes being abandoned, feeding grounds becoming too loud to tolerate. Some species are adapting, shifting their ranges, changing their behavior, but others aren't. Others are just enduring it. And we don't yet know what the long-term consequences will be. Then there are the strandings, mass strandings where dozens or even hundreds of whales and dolphins beach themselves have been recorded for centuries. But in recent decades, the frequency has increased, and many of them correlate with naval exercises, with sonar operations, with sudden bursts of intense sound. The leading theory is that the animals are fleeing, that the sonar pulses are so intense, so disorienting, that the animals panic. They swim erratically. They surface too fast, causing nitrogen bubbles to form in their blood and tissues. Decompression sickness, the bends. And by the time they reach shallow water, they're already dying. Not every stranding is caused by noise, but enough of them are that it's become impossible to ignore. The ocean is no longer a quiet place. It hasn't been for a long time, and the creatures that evolved to navigate it by sound are struggling to cope with the din we've created. But here's the strange thing, the tragic thing. We could fix this, not entirely, but significantly. We could reduce ship speeds, which would lower noise emissions. We could reroute shipping lanes away from critical habitats. We could regulate the use of seismic air guns and military sonar during sensitive periods, when whales are calving or migrating. These aren't impossible solutions. They're practical, achievable. But they require us to acknowledge that the ocean isn't just a resource to exploit or a highway to traverse. It's a living space, a home for creatures that were here long before we were. And right now, we're making it uninhabitable. The ocean still holds its mysteries, the hums and clicks and songs we haven't yet decoded, the calls of creatures we've never seen, the acoustic signatures of geological processes we barely understand. But we're drowning them out, filling the depths with a noise of our own making, a mechanical roar that never stops, never rests, never considers what it might be silencing. The ocean is speaking. It always has been. The question is whether we'll ever quiet down long enough to listen. There are rocks on the ocean floor that look like potatoes, dark, lumpy things the size of grapefruits, scattered across the abyssal plains like a field of forgotten stones. They're called polymetallic nodules, and they contain something humanity desperately wants: metals, cobalt, nickel, copper, manganese. Rare earth elements essential for batteries, electronics, renewable energy technologies. The same materials we need to build solar panels and wind turbines and electric vehicles. The same materials we're extracting from mines on land, often at enormous environmental and human cost. But down there in the deep ocean, they just sit. Millions of tons of them, perhaps billions, waiting. And we're planning to go get them. The age of deep-sea mining hasn't begun yet. Not quite, but it's coming. The technology exists. The interest is there. Corporations have already been granted exploration licenses by the International Seabed Authority, the UN body that regulates the ocean floor beyond national jurisdiction. Test runs have been conducted. Machines the size of combines, fitted with rotating blades and suction hoses, have been lowered to the seafloor to see how efficiently they can harvest the nodules. The results were promising, profitable, feasible, and that's what keeps some scientists awake at night. Because the ocean floor isn't a warehouse, it's not a storage facility where resources just sit inert, waiting to be collected. It's an ecosystem, a living, functioning, unimaginably ancient ecosystem. And we're about to drive industrial machinery through it. The nodules themselves took millions of years to form. They grow slowly, molecule by molecule, as metals precipitate out of seawater and accrete around a nucleus, a shark's tooth, a fragment of shell, anything solid enough to serve as a foundation. The process is so gradual that a nodule the size of a potato might be 4 million years old. 4 million years. That's older than our species, older than most of the fossils we've ever found of human ancestors. These rocks have been sitting on the seafloor since before we learned to walk upright, and we're planning to scoop them up by the ton. But it's not just the nodules. There are other targets, other treasures hiding in the deep. Cobalt-rich crusts coat underwater mountains and seamounts, some of them 10 centimeters thick, packed with metals that took tens of millions of years to accumulate. Mining them would mean scraping the surface of these mountains clean, peeling away layers of mineral deposits like bark from a tree. And then there are the hydrothermal vents, the same vents we talked about earlier, where life thrives without sunlight, powered by chemistry instead of the sun. Those vents deposit metals too: sulfides, copper, zinc, gold. They build chimneys and mounds around the vent openings, structures that are both geological formations and living habitats. And yes, companies want to mine those too. The argument in favor of deep-sea mining is straightforward. We need these metals. Our transition to renewable energy depends on them. Lithium-ion batteries require cobalt. Wind turbines require rare earths. Solar panels require copper. If we're going to move away from fossil fuels, if we're going to avoid the worst impacts of climate change, we need access to these materials. And the terrestrial mines that currently supply them come with their own costs. Habitat destruction, water pollution, displaced communities, child labor in some regions. The environmental damage from land-based mining is well documented and often devastating. So why not look to the ocean? Why not extract resources from a place where proponents argue there are no human communities to displace, no forests to clear, no rivers to poison? It sounds reasonable, almost logical, but it ignores one critical fact. We have no idea what we'd be destroying. The organisms that live among the nodules, on the crusts, around the vents, have evolved over millions of years to survive in one of the harshest environments on Earth. They grow slowly. They reproduce slowly. They exist in a state of such low energy that their entire biology operates at a pace almost incomprehensible to us. A sponge in the deep ocean might live for thousands of years, a single individual filtering water, growing a few millimeters per century. Some deep-sea corals are even older. Specimens have been found that are more than 4,000 years old. They were already ancient when the pyramids were being built. These aren't ecosystems that bounce back. They don't recover on human timescales. They don't recover on the timescales of corporations or governments or economic planning cycles. When you disturb the deep ocean floor, the damage persists for decades, for centuries, possibly forever. We know this because we've already tested it. In the 1980s, scientists conducted an experiment in the Pacific. They dragged a plow-like device across a small section of the abyssal plain to simulate the impact of mining. Then they waited. They returned years later, then decades later. The tracks were still there. The sediment had not settled back into place. The organisms that had been scraped away had not returned. The ecosystem had not recovered. And that was just a small-scale test, a controlled experiment covering a few square kilometers. Industrial mining operations would cover thousands of square kilometers. They would operate continuously, scraping away nodules, grinding up the seafloor, suspending sediment in plumes that could drift for hundreds of kilometers, smothering everything downwind. The impact wouldn't be localized. It would spread, and it would last. But here's the most troubling part, the part that should give us pause. We don't even know what's down there. Remember, we've explored less than 5% of the ocean floor in any meaningful detail. The ecosystems surrounding the nodules, the organisms living in the sediment, the species adapted to the unique chemistry of hydrothermal vents, most of them haven't been studied. Most of them haven't even been discovered. We're talking about mining environments where every expedition brings back new species, where every sample reveals something science has never seen before, where the biodiversity might rival that of tropical rainforests, just expressed in forms we don't yet recognize. And we're considering mining it before we've even finished the inventory. It's like logging a forest before you know what trees are in it, before you know what animals depend on it, before you understand how the ecosystem functions or what role it plays in the larger environment. You wouldn't do that on land. We've learned that lesson. We've seen the consequences of exploitation without understanding. But in the ocean, in the deep, dark, out-of-sight ocean, it seems we're willing to make that mistake again. The companies and governments pushing for deep-sea mining argue that it can be done responsibly, that there will be environmental impact assessments, regulations, protected zones, monitoring. And maybe there will be. Maybe the International Seabed Authority will enforce strict rules. Maybe mining operations will be carefully managed to minimize harm. But even in the best-case scenario, even with the most stringent regulations, the fundamental problem remains. You cannot mine the deep ocean without destroying it, not partially, not temporarily. You destroy it permanently. Because the deep ocean is not like the surface. It doesn't regenerate quickly. It doesn't adapt rapidly. It exists in a state of such profound stability that any disturbance is, by definition, catastrophic. And once you've scraped away the nodules, once you've pulverized the sediment, once you've collapsed the vent chimneys and smothered the surrounding habitats with sediment plumes, you can't put it back. It's gone. The organisms that lived there, gone. The species we hadn't discovered yet, gone. The ecological relationships we hadn't studied, gone. And we'll never know what we lost, because we'll have destroyed it before we even knew it was there. There's a term for this. Scientists call it the unknown cost, the price we pay for acting before understanding, for valuing short-term gain over long-term knowledge, for treating the ocean as a resource to extract rather than a world to explore. And make no mistake, this is a choice. We could wait. We could invest in mapping the ocean floor, in studying the ecosystems, in understanding what we'd be mining before we start. We could explore alternatives, recycling metals from existing electronics, developing batteries that use more abundant materials, reducing consumption. These aren't fantasies, they're options, real, viable pathways that don't require us to gut the least known environment on our own planet. But waiting doesn't generate profit. Understanding doesn't satisfy quarterly earnings reports, and so the pressure to begin mining grows, even as our knowledge of what we'd be destroying remains shamefully incomplete. There's a saying among conservationists, you can't protect what you don't know exists. But the corollary is equally true. You can't mourn what you never discovered. If we mine the deep ocean, if we industrialize the abyss before we've even finished exploring it, we'll lose something irreplaceable. Not just species, though, that would be tragic enough. But knowledge, possibility, the chance to understand an entire realm of life that evolved in isolation under conditions so extreme that its very existence challenges our assumptions about what life can be. The deep ocean is not empty space waiting to be filled with human activity. It's not a blank slate or a warehouse of resources. It's a world, ancient, fragile, and utterly unique. And we're about to decide whether it's worth protecting or whether the metals in its rocks are more valuable than the mysteries in its darkness. The machines are ready, the contracts are being negotiated, the first mining licenses could be issued within years. The only question left is whether we'll have the wisdom to pause, to look, to understand what we're about to do before the sediment plumes rise and the nodules disappear and another frontier closes forever. Chapter 7. The Ocean. Inside us. There's something deeply human about looking up. We've always gazed at the stars, told stories about them, mapped them, given them names and meanings. We've wondered what lies beyond the horizon of our atmosphere, beyond the reach of our world. The sky has been a canvas for our dreams, our myths, our ambitions. And when we finally developed the technology to leave Earth, we didn't hesitate. We launched ourselves into the void. We planted flags on the moon. We sent machines to Mars, to Jupiter, to the edge of the solar system, and beyond. We chose distance. We chose the impossible. We chose up, but we never chose down. Why is that? Why does the distant call to us more powerfully than the immediate? Why do we dream of colonizing Mars when we haven't yet explored our own ocean? Why do we search for life on the moons of Saturn when we're still discovering new forms of life in our own trenches? The practical answers are real. Space offers tangible goals: a footprint on the moon, a rover on Mars. These are achievements we can photograph, celebrate, point to as evidence of human capability. The ocean offers no such clarity, no flags to plant, no horizons to cross, just depth and darkness, and the humbling realization of how much we don't know. But there's something deeper at work, something psychological, perhaps even spiritual. We are drawn to what we can see, and we avoid what forces us to confront our limitations. Space is vast, yes, incomprehensibly so, but it's also empty. It's distance without density, a void we can cross with the right velocity and the right protection. It challenges our engineering, our mathematics, our courage, but it doesn't challenge our sense of ourselves. The ocean does. The psychologist Carl Jung wrote about the unconscious, the hidden parts of ourselves we don't acknowledge, the fears, the desires, the aspects of our nature we bury because they're too uncomfortable to face. He called it the shadow, the part of us that exists in darkness. And he suggested that we project these hidden aspects onto the world around us, that we see in external landscapes the internal territories we're afraid to explore. The ocean, in this sense, is more than just water and salt and pressure. It's a symbol, a physical manifestation of everything unknown, everything uncontrolled, everything that resists our understanding. The abyss isn't just a place, it's a mirror. When we look down into the deep ocean, when we contemplate its crushing pressure and its impenetrable darkness, we're confronting something primal, something older than language or civilization or conscious thought. We're confronting the unknown itself, and we don't like it. Humans are creatures of light and air. We evolved on land under an open sky, in environments where vision was our primary sense. We built our entire civilization on the assumption that seeing is knowing, that what's illuminated can be understood, that what's visible can be controlled. But the ocean operates on different principles. It's a realm where vision fails, where light dies, where sound becomes the primary language and pressure replaces gravity as the dominant force. It doesn't care about our assumptions. It doesn't accommodate our senses. It simply exists, indifferent to whether we understand it or not. And that indifference is terrifying, because it reminds us that we are not central. We are not the measure of all things. We are just one species, adapted to one narrow set of conditions, trying to make sense of a planet that existed for billions of years before we did and will continue long after we're gone. The ocean humbles us, and perhaps that's why we avoid it. It's easier to look at Mars and imagine ourselves as pioneers, as explorers conquering new frontiers. It's harder to look at the ocean and accept that we're still strangers on our own world, that there are places here, not light years away, but just kilometers down where we don't belong, where we can't survive, where nature operates according to rules we're only beginning to understand. Hubris tells us to reach for the stars. Humility suggests we should first understand the ground beneath our feet, or in this case, the water. But there's another layer to this, another reason the ocean unsettles us. It's not just unknown, it's familiar. We came from the ocean, all of us, not just as a species, but as individual organisms. Every human being begins life in a fluid environment, suspended in amniotic water, nourished through an umbilical connection, existing in a state of pressure and darkness not entirely unlike the depths. We carry the ocean inside us, literally. The salt concentration in our blood is remarkably similar to seawater. Our cells are bathed in fluid. Our bodies are 60% water. We are, in a very real sense, walking oceans, landlocked, contained, but still fundamentally aquatic. And perhaps that's why the deep ocean feels so uncanny. Not alien, not truly foreign, but disturbingly familiar. Like returning to a home we've forgotten, a place we left behind but never entirely escaped. The ocean is our origin, the cradle of all life on Earth, the environment where the first cells formed, where the first organisms learned to metabolize and reproduce and evolve into everything that followed. 4 billion years ago, life began in water, probably near a hydrothermal vent in the crushing darkness of the ocean floor. And from that single origin, everything branched out. Fish, amphibians, reptiles, mammals, plants, fungi, us. We are all, every living thing on this planet, children of the ocean. But we've forgotten that. Or maybe we've chosen to forget it. We tell ourselves we're terrestrial, that we're creatures of the land, that we've transcended our aquatic origins and become something separate, something independent. But stand at the edge of the ocean and listen to the waves, and something in you remembers, something deep and wordless, an echo of a time before lungs, before legs, before the evolutionary leap that brought our ancestors onto dry ground. The ocean isn't just out there, it's in here, in our cells, in our chemistry, in the deepest, oldest parts of our biology. And that connection matters, because our relationship with the ocean isn't just scientific or economic or environmental, it's existential. We don't just depend on the ocean for oxygen, for climate regulation, for food and resources. We depend on it for context, for understanding where we came from and what we're part of. The ocean reminds us that we're not separate from nature. We're embedded in it, shaped by it, sustained by it. And right now, we're treating it with the carelessness of strangers. We pollute it, we overfish it, we warm it, we acidify it, we fill it with noise and plastic and chemicals. We mine it before we've even begun to understand it. We take from it endlessly and give back only waste. And we do this, in part, because we don't see it. We don't live in it. We don't encounter it daily in ways that force us to acknowledge its fragility or its importance. But ignorance is a choice. Neglect is a choice. And the consequences of those choices are becoming harder to ignore. The ocean is changing, warming, losing oxygen, becoming more acidic. The ecosystems we've barely begun to study are already shifting, already adapting, or failing to adapt to conditions that are changing faster than they've changed in millions of years. And we're the cause, not intentionally, not maliciously, but undeniably. We are altering the ocean, the system that gave birth to us, the environment that continues to sustain us, and we're doing it without fully understanding what we're changing or what we stand to lose. This is the paradox. This is the tragedy. We have the capability to explore space, to send robots to other planets, to detect gravitational waves and photograph black holes and map the cosmic microwave background. But we haven't figured out how to protect the ocean we depend on. We can land a rover on Mars with pinpoint precision. But we can't stop plastic from accumulating in the deep sea. We can listen to the echoes of the Big Bang. But we can't quiet the industrial noise that disrupts whale communication. We can dream of colonizing other worlds, but we're destroying the one we have. And maybe that's because exploring space feels aspirational. It feels like progress, like humanity reaching toward something greater. But confronting the ocean? That feels different. That feels like accountability, like reckoning with the mess we've made, like admitting that we've been reckless with something irreplaceable. It's easier to look up than to look down, easier to dream of Mars than to face the Mariana Trench. But the ocean won't let us off that easily, because our future is tied to it, not metaphorically, not philosophically, but literally. If the ocean's circulation collapses, our climate destabilizes. If the biological pump fails, carbon accumulates faster in the atmosphere. If methane hydrates release, warming accelerates beyond our ability to control. If we mine the seafloor before understanding it, we lose knowledge we can never recover. The ocean is not a side issue. It's not secondary to space exploration or technological innovation or economic growth. It's the foundation, the context, the system within which everything else exists, and we're ignoring it. Not because we don't care, but because caring requires humility. It requires us to admit that we don't understand, that we've been careless, that we need to change. And change is hard, especially when it means turning away from the stars and looking instead into the depths, into the darkness, into the mirror that reflects not what we want to be, but what we are: finite, dependent, connected. The ocean doesn't need us. It existed for billions of years before we arrived, and it will exist long after we're gone. But we need it. We need it to breathe, to eat, to live, to survive. And maybe that's the lesson, the reason we've avoided the ocean for so long, because understanding it means understanding ourselves, our vulnerability, our limits, our place in a system far larger and far older than we can fully comprehend. The ocean is our origin, and if we're not careful, it will also be our reckoning.